Hello, good morning, good afternoon, everybody. So today topic is Unit 9, a ring of fraction. So this is a ring of a fraction is a ring of a fraction. So it's a clear. Ring of a fraction, regular element. Let R be a commutative ring with unity. Then a non-zero element A belongs to R is said to be regular element if A is not a zero divisor. Class చెప్తున్నా వస్తున్నా హాఫ్ అన్ అవర్ వస్తుంది hello it is A is a not a zero divisors. A not zero divisors is meaning A not equal to 0, B not equal to 0. This is simple as AB equal to 0. AB equal to 0. This is a zero divisors. This is not a zero divisors is meaning suppose Z4 addition model of 4 multiplication model of 4. Z4 is equal to 0, 1, 2, 3. So 1, 2, 3 addition model of 4 multiplication is a zero divisors is meaning is GCD. So 2, 4 GCD not 2, 4 GCD is equal to some 2. Then what is a zero divisors is 2, 4 GCD something not equal to 1. 0, 4 0, 4 only. So 1, 4 not equal to GCD 1. 3, 4 not equal to GCD 1. Only zero divisors. Only zero divisor is 2. Only zero divisor is 2. So only zero divisor is 2. Now again, it is 1, 3 is a not a zero divisors. 1, 3 are regular elements. Regular elements. So 1, 3 Z plus comma dot is a ring of non-zero divisor. Every non-zero element in Z is a regular element. Every non-zero element Z is a regular element. Next example is this is Z6 addition model of 6 and multiplication model of 6. Z6 is equal to 0, 1, 2, 3, 4, 5 is addition model of 6 multiplication of 6 or 2, 3, 4 are zero divisors and 1, 5 are regular or non-zero divisors. 1, 5 non-zero divisors are regular elements. Regular elements. So regular elements. 1, 2, 3, 4 GCD. 2, 3, 4 GCD is some not equal to 1. So it is a 2, 3, 4 zero divisors. Next is multiplicative set. These are definition is called is multiplicative set. A non-empty subset of a ring R is said to be multiplicative set if S is closed with respect to multiplication. If S is closed with respect to S1, S2 belongs to capital S. S1, S2 belongs to capital S. So this implies so S1, S2. So S1, S2 belongs to capital S. So it is called as a consider Z plus comma dot. So this is a Z plus comma dot. This is so it is a consider. So consider the ring Z plus comma dot. Let S is equal to 0 plus or minus 2 plus or minus 4 plus or minus 6. Here S1, S2 belongs to S. For all S1, S2 belongs to S. S is a multiplicative regular set, multiplicative set. S is equal to 0, plus or minus 1 plus or minus 3 plus or minus 5 plus or minus 7 is a multiplicative set. S is equal to 0 plus or minus 2 plus or minus 3 plus or minus 5 plus or minus 7 plus or minus 7. So plus or minus 7. plus or minus 7 is not a multiplicative set for S1 is equal to, for S1 is equal to, we taken for S1 is equal, so simplify that, for S1 is equal to, S1 is equal to, S1 is equal to 2, S2 is equal to 3, S1, S2. So S1, S2 is equal to 2 into 3 is equal to 6. Does not belongs to S. 2 is does not belongs to regular, a non-empty subset of S of a ring, or a non-empty subset of a non-empty subset of a non-empty subset S of a ring R is said to be regular multiplicative set if S is multiplicative. A non-empty regular multiplicative set, a non-empty subset of a ring R is said to be regular multiplicative set. S is multiplicative. Second, every non-zero element of S is a regular element. Every non-zero element of S is a regular element. What is a regular element is example. S is equal to 0, 0 comma plus or minus 2, 0 comma plus or minus 2. This is 0 comma plus or minus 2, plus or minus 4, plus or minus 6, plus or minus 6 up to 7. So S is equal to 0 comma plus or minus 1, plus or minus 3 up to 7. The regular multiplicative set in Z comma plus comma dot, in Z comma plus comma dot. This is a, so what is it today? It is a clear from. Next theorem. This is a R is a integral domain. Then the R is integral domain. So this theorem is R is integral domain, then S R minus singleton 0 is a regular multiplicative set. Proof. Given that S is an given that R is integral domain, A not equal to 0, comma B not equal to 0. This is implies AB not equal to 0. AB not equal to, for all A comma B belongs to R. This R is without 0 divisors. R is without 0 divisors. So R is without 0 divisors. R minus singleton 0 is without 0 divisors. Every element of R minus singleton 0 is a regular element. This is the equation 1. Now regular element, this is equation 1. Let regular element. So regular. So it is S1 comma S2 belongs to R minus singleton 0. So this is a S1 is not equal to 0. S1 is not equal to 0. S1 is not equal to 0. S2 is not equal to 0. S2 not equal to 0 belongs to R. This is S1 comma S2 is a belongs to R, and S1 S2 is a does not belongs to R. S does not belongs to R. So S1 S2 belongs to R minus singleton 0. R minus 0. So here equation number 2, multiplicative set. From 192, we got a regular multiplicative set. So this is regular multiplicative set. Now again, no, this is a notice. Here, let R be a commutative ring. Let R be a commutative ring. R be a commutative ring. R be a commutative ring. S be a multiplicative set in R. Then a relation. This relation depend on R cross capital S. R cross capital S as first one is. This is the reflexive is R comma S is equivalent to R1 comma S1. So this is if and only if there exists some t belongs to S such that t into rs1 minus r1s is equal to 0. R1s is equal to 0 is an equivalency relation. So is an equivalency relation. So first one is a proof. Reflexive. So what is a reflexive property? Equivalence relation satisfied? No. Reflexive, symmetric, and transitive. That is called as a equivalency relation. So R1 comma S belongs to R cross S. R S minus RS is equal to 0. R comma S belongs to. T belongs to. For T belongs to S, T into RS minus SR equal to 0. T into 0 equal to 0. And this is same set. R1 plus in S, S1. R comma S belongs to R Cartesian product S. RS minus SR equal to 0. For T belongs to S. So for T into RS minus SR equal to 0. So this is RS comma is equivalent to SR. So this is a reflexive. It is a reflexive. It is a reflexive. Now again, symmetric. So what is the symmetric is R1 comma S1 comma R2 comma S2 belongs to R cross S. R cross S. So the relation is R1 R1 comma S1 related to R2 comma S2. There exists T belongs to S. T into R1 S2 minus R2 S1 is equal to 0. There exists T belongs to S such that minus T into R2 S1 minus R1 S2 is equal to 0. So totally we have to that minus T belongs to S minus T into R2 R2 S1 minus R1 S2 equal to 0. And this is the relation R2 comma S2 is equivalent to R1 comma S1. R1 comma S1. Transitive. What is the transitive is R1 comma S1 is equivalent to R2 comma S2. R2 comma S2 equivalent to R3 comma S3. This is the R1 comma S1 is related to R2 comma S2. What is the according to definition? T belongs to S. T1 belongs to S into T1 into R1 S2 minus R2 S1 is equal to 0. T2 belongs to S. So T2 into R2 minus S R2 T2 into R2 minus R2 S3 minus R3 S2 is equal to 0 from 1 and 2. So one equation should product. One equation multiplication T2 T3 and second equation multiply T1. So we can do one equation adding like this. So one equation T2 S3 and second equation T1 S1 we can adding. This is a totally the result is T2 T3 T1 into R1 S2 minus R2 S1 is equal to 0. Next to T1 T2 to T1 S1 T2 is equal to R2 S3 minus R3 S2 is equal to 0. By adding, we get this is a T2 S3 T1 into R1 S3. So minus T1 S1 T2 into R3 S1 is equal to 0. So we have to or like this T2 T1 S2 into R1 S3 minus R3 S1 is equal to 0. That is a relation R1 comma S1 is equivalent to R3 comma S3. So this is a relation is called is a equivalence relation, is an equivalence relation, is an equivalency relation. So this is an equivalency relation. So equivalent. Since relation, this equivalence relation on R comma S, it divides R comma S into designed equivalent classes. Let R by S the equivalent classes of R comma S belongs to R comma S is equal to the equivalent classes of R comma S. Okay, this is the result is R1 comma S1 belongs to R comma S such that R1 comma S1 belongs to R comma S. So this is the equivalent relations. Now again, నడుస్తుందా అప్లాన్ కన్నడ వేసిరా అక్కడ కిచెన్ మూమెంట్ పడతాడు కొంత సోలో ఆ పిల్లలు అరవ కాక చెప్పండి ఇక్కడ వాళ్ళు డిస్టర్బ్ ఏం లేదు పిల్లలు అరుస్తున్నది డిస్టర్బ్ లేదు ఏ మనకు చిన్న ఫస్ట్ స్వీట్ తీసుకురా తర్వాత స్వీట్ కాడ ఎవరు ఉన్నారు చూసి సార్ మంది ఉంటారు మళ్ళీ బాబు కాడ చెప్పి తీసుకురా అన్ని తీసుకెళ్ళకు ఫస్ట్ సీట్ ఓకే ఆడబెట్టుకో బాబు అనుకుంటారు theorem is Rs. This is R by S, such that R belongs to R, smallest belongs to capital S. So be the set of all equivalent classes and R, S. Define a relation, addition and multiplication on Rs as R1 by S1 plus లోపల స్వీట్ చికెన్ వేసిరా ఎవరైనా పిల్లలు ఏమైనా అన్నారా R1 by S1 plus R2 by S2 is equal to S2. So R1 by S1 plus R2 by S2 is equal to it is a operation R1 S2 plus R2 S1 by S1 S2 S1 S2. This is a product R1 by S1 dot product R2 by S2 is equal to R1 R2 by S1 S2 S1 S2. So R plus comma dot a commutative ring with unity RS. This is RS plus comma dot a ring of fraction with respect to commutative ring with unity. So commutative to show that. This is the theorem 9.3.9. 9.3.9. So 9.3.9 commutative ring with unity. So commutative 9.3.9 this theorem also. So we can call it is a plus R comma S ring of fraction plus is an abelian group. Is an abelian group. So is an abelian group. So abelian group first one is Addition is a closure. R1 by S1, comma R2 by S2 is a belongs to a ring of fraction RS. R1 by S1 plus R2 by S2 is equal to R1 S2 plus R2 S1 by R S1 S1 S2 is a belongs to RS. So closure. Next is a associate property. What is the associative property? R1 by S1 plus R2 by S2 plus R3 by S3. R3 by S3 is equal to R1 by S1 plus R2 S3 plus R2 S3 R3 S2 by S2 S3 S2 S3. So we have to taken either total LCM. Total LCM is S1 into S2 S3 total LCM. What happened situation? R1 into S2 S3 plus S1 into, so this is S1 into R2 S3 plus R3 S2. So this is a clear now. Is equal to R1 S2 S3 plus R2 S3 S1 plus R3 S1 S2 by S1 S2 S3. So we are from using question 1. This is LHS. What is the RHS is? LHS is a clear. So equation 1. This is LHS. I'm taken from LHS. What is the RHS is a clear. RHS is this way. RHS is RHS is a clear. R1 by S1 plus R2 by S2 bracket plus R3 by S3. This is a simplified that same result. What happened is, so it is a clear from S1 S2 first fraction LCM. So R1 S2 plus R2 S1. So R2 S1 plus R3 by S3. R3 by S3. So is a total LCM is a taken S1 S2 S3. So we have taken R1 S2 S3 plus R2 S1 S3 plus R3 S1 S2. R3 S1 S2. It's a clear. LHS is equal to RHS. LHS is equal to RHS. So it's a clear. So this is associative property addition. Now it is a 0 for 0 belongs to RT. 0 by S is belongs to RS. The identity element of a ring fraction 0 by S. 0 by S. So 0 by S. So this is R1 by S1 plus 0 by S is equal to R1S plus R1S plus 0 into 0 into S1 by SS1. So is equal to R1S by S1 SS1. So it is a SS is a ring of fraction R by S1. R by S1. So R by S1. So R1 by S1. Similarly, 0 by S plus 0 by plus R1 by S1 is equal to R1 by S1. R1 by S1. So 0 by S is a zero element. Is zero element in RS. In zero element in RS. So this is called as A4. So it is a for R by S belongs to R by S. R by S belongs to a ring of fractions. Minus R by S belongs to RS. R comma minus R belongs to S. R by S plus minus R by S is equal to RS plus minus R into S by SS is equal to RS minus RS by SS is equal to 0 by S. 0 by S. So 0 by S. This is called similarly. So what is the similarly? Minus R by S plus R by S is equal to 0 by S. Minus R by S is the inverse of R by S. Inverse of R by S. So inverse of R by S. So A5. So this is LHS is A5 abelian group R1 by S1 plus R2 by S2 is equal to, it is a LCM is S1 S2 R1 S2 plus R2 S1. So R2 S1. So this is S1 S2 R2 S1 plus S1 R2 by S1 S2 S1 S2 is equal to, this is a simplify, it is a simplify that R2 by S2 plus, so simplify same thing, R2 by S2 plus R1 by S1. So therefore abelian property R1 by S1 plus R2 by S2 is equal to R2 by S2 plus R1 by S1. This is the addition of a fraction of abelian group. Totally, this is called as, which is a simplify that, it is a RS simplify that. This is RS simplify that. RS R by RS comma plus is an abelian group. Is an abelian group. So is an abelian group. So abelian group. So next is RS comma semi group. So RS comma dot is semi group. Is a semi group. Is a semi group. Is a semi group. So RS comma dot is a semi group. R1 by S1 comma R2 by S2 belongs to RS. So is a RS. So R1 R2 R2 by S1 S2 belongs to RS. This is called is a multiplication closure. Multiplication closure property. Multiplication associative property. Multiplication associative property. This is R1 by S1 comma R2 by S2 comma R3 by S3 belongs to a fraction ring of S. R1 by S1, the product of R2 by S2 dot product of R3 by S3 is equal to R1 by S1, the product of R1 R3 by S2 S3. So R1 into R1 R2. This is R2 R1 into R2 R3 by S1 S2 S3. This is a simplify that. So is a clear that R1 R2 bracket R3 by S1 S2 bracket S3. So this is a again simplify that R1 R2 S1 S2 is our dot product of R3 by S3. This is RS comma dot is a semi group. Is a semi group. So is a semi group. So this is a semi group. Now distributes R comma S distributes class R1 by S1 dot R2 by S2 plus R3 by S3. So R3 by S3 is equal to R1 by S1. So this simplified R2 S3 plus R3 S2 by S2 S3. We out product. Simple S2 S3. This is a product is a simplified like that. So it's a clear. What happens situation? R1 R2 S3 plus R1 R3 S2 by S1 S2 S3. This is a third equation. So simplify next to, it is a simplify that it is a RHS is R1 by S1 R3 by S2 product plus R1 by S1 R3 by S3. So R2 by S2. This is R2 by S2. This is R1 by S1 R2 by S2 plus R1 by S1. So R3 by S3. So this is a simplify. This simplify it take an LCM also. Total LCM S1 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 S2 S3. So this is R1 S2 into S1 S3 plus R1 R3 S1 S2. So S1 S2. So it is a clear from division from S1, S3, simplify that R1, R2, R1, R2, S3. We take an S1 is common, is cancel them. So R1, R3, S2. So R1, R2, S3. By third and fourth is a third four. Similarly, we can do right distributist property. R1 by S1 plus R2 by S2 into R3 by S3. R1 by S1 by R3 by S3 plus R2 by S2 into R3 by S3. So it's called R plus comma RS plus comma dot is a ring. So this is a distributive slot satisfied is a ring. This ring is also RS is a commutative ring. Is commutative ring. This is a commutative. So commutative ring. So what is a commutative is called is R1 by S1 into R2 by S2 is equal to R1 R2 by S1 S2. So this simplify R2 by S2 into R1 by S1. So R2 by S2 into R1 by S1. R1 by S1. So it is a semi-group. This is called as a semi-group. It is a commutative property. A fraction ring is called as a commutative property. So it is RS as a unity element, as unit element. So unit element. For 1 belongs to R, so S by S belongs to RS fraction ring. So RS by S by S is equal to S by RS by SS is equal to R by S. So R by S. It's a clear. So చిన్న పెద్దదా చిన్నదా వాళ్ళకు ఏమో తెలియదు స్టోర్ S is a multiplicative set in a commutative ring. S is a multiplicative set in a commutative ring, or then there exists a natural homomorphism. F is mapping from R to RS. So R to S defined by F of A is equal to AS by S. AS by S. For all A belongs to R, A belongs to R, smallest belongs to capital S, smallest belongs to capital S. Proof. Let A comma B belongs to R, A comma B belongs to R. F of A is equal to AS by S, AS by S. F of B is equal to BS by S, BS by S, where smallest belongs to F of A plus B is equal to A plus B is A plus B of S by S, S by S, AS plus BS by S. So AS by S plus BS by S. So this is F of A plus F of B, F of B. So your second condition. F of AB is equal to, so AB of S by S. So we have to write here AB into S by S is S by S unity element. Now simplify that AB of SS by SS by SS. So we have to AS into BS by SS. It takes separately, same thing. So AS by S into BS by S. This is F of A into F of B. F of A into F of B. So F of A is F of B. So it's a clear now. If a F of A. So this is, so it's a clear from now. F is mapping from R to RS. R to RS. R to RS is a homomorphism. Is a homomorphism. So homomorphism, which is called, which is called, which is called, so which is called natural morph, which is called natural homomorphism. Natural homomorphism. Natural homomorphism. Natural homomorphism. So it is a clear from local ring. So what is a local ring definition? A ring R with unity element, unity is said to be a local ring if it has a unique maximal left or right ideal. A unique maximal left or right ideal is called a ring R with unity is said to be a local ring if it has a unique maximal left or right ideal. So theorem. So it is R be a commutative ring and P be a prime ideal. Then the set S is equal to, then the set S is equal to R minus P is a multiplicative set, is a multiplicative set, is a multiplicative set. Second condition, this is the second condition. What is the second condition is the ring RS, the ring RS is a local ring, is a local ring, is a local ring with unique maximal ideal, with unique maximal ideal. So unique maximal ideal in PS is equal A by S such that A belongs to P and S belongs to capital S. S belongs to capital S. So given that uh, given that P is a prime ideal, given that P is a prime ideal, is a prime ideal of a commutative ring R. Let S is equal to R minus P. Let S is equal to R minus P. So first one, it is a we prove that S is multiplicative set. We prove that S is a multiplicative set. A multiplicative set. This is A comma B belongs to S, R minus P. A comma B belongs to R, and S R minus P and this means A comma B does not belongs to P. So for A comma B belongs to R, we know that AB belongs to R. R is a ring, a closure property. R is a ring with a closure property. So with a closure property. So if it possible, suppose AB belongs to P. If it possible, possible, suppose AB belongs to P. So AB belongs to P. A belongs to P or B belongs to P. So P is a prime ideal, which is a contradiction. So for A comma B not equal, A comma B does not belongs to P. AB does not belongs to P. AB belongs to R and AB does not belongs to P. So AB belongs to R minus P. AB belongs to R minus P. AB belongs to R minus P. AB is a belongs to S is a multiplicative set. S is equal to AB belongs to R minus P. This is a nothing but AB belongs to S. A comma B belongs to S. AB belongs to S. This set is called as multiplicative set. AB belongs to S. S is a multiplicative set. I am starting is there. It is A comma B belongs to S. You can show me AB belongs to S. S is a multiplicative set. Second condition. It is a second one. So it is a second. Since S is a multiplicative, RS is equal to R by S such that R belongs to R, smallest belongs to capital S, is a commutative ring with unity. Commutative ring with unity. Define a relation. So define a relation PS. So define a relation PS. So this is a relation PS is equal to, so A by S such that where A belongs to P, S belongs to capital S. S belongs to capital S. Clearly, this is a clearly PS subset are equal to RS. PS is subset are equal to RS. PS is equal subset are equal to RS. We prove this PS is an ideal. We prove PS is an ideal. We prove PS is an ideal. So PS is an ideal is means A1 by S, A2 by S belongs to PS, belongs to PS. Consider A1 by S minus A2 by S is equal to A1 by S plus of minus A2 by S is equal to, this is a simplify S, so S LCM A1 S minus A2 half S is equal to A1 minus A2 of S. So belongs to PS. So belongs to PS. This is called is now again A1 minus A2 belong by S is a belongs to PS. Is a belongs to PS. Same thing. A1 by S belongs to PS. Okay. R by S belongs to RS. So RS. We have A1 by S dot R by S is equal to A1 R by SS. So is a belongs to PS. Is a belongs to PS. Is a belongs to PS. So this is a PS is maximal ideal. PS is an ideal. So is an ideal. So is an ideal in RS. So in RS, we prove that. So we prove that PS is a maximal ideal. We prove that PS is maximal. P is a prime ideal since P is a prime ideal since P is a prime ideal. P is a prime ideal in R. So P is subset not equal to R implies there exists R belongs to R such that R does not belongs to P. R by S belongs to RS and R by S does not belongs to PS. So this is a called issue. PS is a subset are equal to PS subset not equal to RS. So this implies since R does not belongs to P, R belongs to capital R. So this implies R belongs to S. S by R belongs to RS. So S by R belongs to RS. So simplify that S R by S by R is belongs to RS. So RS by SR is a belongs to RS. SS by S. So belongs to RS. So RS. Every ఆ ప్యాకెట్ ఇచ్చిన నీకు పులివర్ ఇప్పుడు ఏం కడతలేరు కదా ఓకే ఓకే ఇఫ్ నౌ RS by SR is a belongs to RS. So RS by SR is a belongs to RS. SS by S belongs to us. Every it is every RS by does not belongs to PS. So has a a multiplicative set, has a multiplicative set, multiplicative inverse, multiplicative. BS, suppose BS is any ideal, BS is any ideal, so this is ideal in RS, in RS. Okay, this implies, so PS is subset or not equal to BS subset or equal to RS. So we prove that, we prove that we prove that BS is equal to RS, BS is equal to RS. So therefore PS is subset of, PS is a subset of, PS is a subset of BS. So PS is subset of BS. There exists, so PS is a subset of BS. So there exists is A by S belongs to BS. So and AS by does not belongs to PS. So since A by S does not belongs to PS, by above conclusion, A by S has multiplicative inverse in S by A. Multiplicative inverse S by A. That is the means A by S dot S by A is equal to S by A dot A by S is equal to S by S. Here equation number 1. So equation number 1. So A by S belongs to BS. S by A belongs to RS. RS. We have A by S dot S by A belongs to BS. BS is ideal. Is ideal. So this is a ideal. So BS is ideal. So that is S by S belongs to BS. So it's a called is B by S belongs to RS. For S by S belongs to BS, B by S belongs to RS, S by S into V by S belongs to capital BS. V is a ideal, BS is a ideal. So B by S belongs to B by S belongs to B by S. So cut we know that. After what is the RS is subset or equal to BS. So but we know that BS is subset or equal to RS. Every ideal is a subset of R. So BS is equal to RS. BS is equal to RS. PS is a maximal ideal. Is maximal in RS. We prove that. Next time, this is we prove that. So we prove that PS is a unique maximal ideal. Already PS is a maximal in RS. We have PS is a maximal in RS. We have to prove that PS is a unique maximal ideal. Unique maximal ideal. So this is now UB any other ideal, UB any other ideal, other maximal ideal in RS, in RS. So U not equal to RS. If it possible, suppose that U not equal to PS, U not equal to PS, then there exists B by S belongs to U, such that B by S does not belongs to PS. So BS by does not belongs to PS. So by above conclusion, B by S as a multiplicative inverse in S by B. So in RS. So in RS. So we can do right too. This is B by S belongs to U. S by B belongs to R by RS. So B by S into S by B belongs to U is ideal. This is S by S belongs to U. So S by S is a belongs to U. U is an ideal in RS. We have U is equal to RS. So U is equal to unit element and up to U is equal to RS, which is a contradiction. So equation number 2, U is equal to PS. PS is a unique variable in R by S. PS is unique variable is RS. So local ring definition. What is a local ring definition is called is a ring R with unity set to be local ring if it has unique maximal ideal. If it has a unique maximal ideal, so unique maximal left ideal right ideal is called is local ring. So local ring. So this way now again. Now, next is a direct sum topic is వచ్చి పక్కన అక్కడే పెట్టాడు ఆడ రూమ్ లెక్కలను దేనికైనా నాన్న ఆడ చేసి కొద్ది చికెన్ లేదా అది ఉంటే direct sum definition 6.4.1. is 6.4.2 theorem. 6.4.2 theorem is let this is R be a ring, R be a ring. So R be a ring, R be a ring. This is Mi is such that I belongs to capital I. Will be a classes of R model. Then there exists a direct sum, a direct sum, a direct sum, a direct sum of, a direct sum of, a direct sum of capital Mi is such that I belongs to capital I is the essentially unique of the following sense. So Mi of Fi is I belongs to. This is Mi of Fi of like this, such that I belongs to capital I. So Mi next is capital Mi dash. This is Fi dash is a direct sum of this thing. Capital M is isomorphic to M dash. So and there exists R of R homomorphism. There exists R homomorphism. R homomorphism is F is mapping from M to M dash, such that F circle of Fi is equal to Fi dash, Fi dash for all I is belongs to capital I. So same, it's a proof. This is a proof is it's a proof is like that. It is a meaning of like that. It's a meaning of like that is capital M to capital M to M, capital M to M, Fi to M dash. So this is M dash to that. This is M dash. This is Fi dash Fi. So let M is equal. Let M is equal to. So this is X such that I subset of union of I belongs to I is a Mi. So such that Xi of I is a belongs to Mi. So Mi. So ikkada Xi of is equal to 0 for but not infinite. So X belongs to M. This is a mod X is equal to. So I belongs to capital I such that Xi of is not equal to 0 is called the support X. Note that M is a subset of this Cartesian product Mi dash. M consists all X who support mod X is finite subset. We shall make M R modulo define the operation follows. For an X comma Y belongs to M, A belongs to define X plus Y. So X plus Y of I is equal to X of I plus Y of I. So Y of I. So alpha of X of I is equal to A of X of I, A of X of I. So it's a clear from no. Mod X plus Y is subset or equal to mod X union mod Y. Mod of AX subset or equal to is a mod X. Suppose this is a X is a finite, minus of X of I is equal to minus of X of I. This for all I belongs to I. So it is a clear from again now define the function is now define function is Fi is a mapping from Mi to M. So M2 as follows for Xi belongs to A. Fi of Xi is of J is equal to is Xi if J is equal to high. This is 0 if J not equal to high. J not equal to high. Now we are Fi is R homomorphism. N is N R modulo M. So N is R modulo M. Gi is a mapping from Gi is a mapping from Gi is a mapping from Mi to capital N is a R homomorphism. R homomorphism. Then we define G is a mapping from capital M to N defined by G of X is equal to summation of I belongs to I. So G I of X of I, G of X of I for all X belongs to capital M. So for all X belongs to. through the I is actually so g of x. So g of x is equal to summation of I belongs to mod of x. So g I of x of I, g of x of I for all x belongs to capital N. So like that. So x comma y is a clearly x comma y is a belongs to capital M. So a comma b belongs to R real number. Here g of ax plus by. G of ax plus by is equal to summation of I belongs to I. So gi of ax plus by of I. So by of I is equal to, this is summation of I belongs to I, gi of ax of I plus by of I. So by of I. So summation of I belongs to I. So I belongs to I. So ag of xi. So it's a clear ag of xi, agi of xi plus bgi of yi, bgi of yi. So yi, this is called is indirectly ag of x plus bg of I. It's a linear. It is a homomorphism. So R homomorphism. Hence G is a g of ax plus by. So plus by is equal to a into g of x plus b into g of y. So since G is a R homomorphism, R homomorphism also. So G circle of f of I of xi is equal to g of f of I of xi. So is equal to summation of I belongs to I, gi of fi of xi. So xi, this is of j is equal to gi of xi. ఎందుకంటే therefore j not equal to I 0. So g circle of f of I is equal to gi. So g dash is a mapping from so m to n. So m to n is any homomorphism, so such that g dash circle of f of I is equal to gi for all I belongs to I. Then you can easily check them. So is equal to, this is g dash is equal to gi. So hence this is the direct sum of, so this is a called is, hence it's a clear from m dash of f f dash of I. This is a mapping from I belongs to I is a direct sum of, is a direct sum of, is a direct sum of, direct sum of, so m I of such that I belongs to I. So I belongs to I. Say no. We prove the uniqueness of m dash of I, f I dash is a direct sum. Then we shall prove that m and m dash is isomorphic. So we said m dash is a unique also. We shall m and m is isomorphic to m dash. So m dash to be n, m dash to be n, and to be n to f fi dash. So fi dash. So to be gi. So to be gi. So is a homomorphism. So f dash of mapping from capital M to m dash. So such that f circle of f dash of I is equal to f of I. So I belongs to I. Then f circle of f dash of I. So it is a circle of f of I. So f circle of f dash circle is f dash of circle I. So this is f circle of f dash circle of I is equal to f of I for all I belongs to I. So similarly, same thing. Now f circle of f dash of circle of f of I is equal to fi. So is equal to identity R modulo circle of f of I Rahala. So this is called as a diagram also. Now it is so it is m to m. So m to m. So this is called as m dash. So m dash. This is called as m also. So it is a clear from. It is a clear from. So f dash. This is a mapping from f dash. This is a mapping. It is a circle from f. So f circle of g dash. So this is a mapping from fi. This mapping from fi dash. This is mapping from fi. So this is mi is also. So mi to mi dash, mi to m, mi dash to m. It's a now given. This is a theorem. It's also it is a direct sum of theorem. Now again. So 7.4 topic is free models. Free models. Free models. Linear independence, linear dependence. A finite set x1, x2 elements R models. This is a finite set. A finite set. A finite set x1, x2 up to son xn of elements of and R models. R modulo m is said to be li a1x plus a2x2 plus up to son an plus an xn is equal to 0m. So then a1 is equal to a2 is equal to up to son is equal to an is equal to 0 half where a is belongs to us. అక్కడ వర్క్ అయిపోతే ఇంకా నడుతుందా మిస్ కలుపుతున్నారా ఓకే ఆ ప్యాకెట్లు తీసుకుపోయి ఇచ్చినావా ఎన్ని 3 ఇచ్చినావా 4 ఇచ్చినావా 5 ఇచ్చినావా ఏ 4 చెప్పాను 2 తీసుకురా సో దిస్ ఇస్ అ బి linearly dependent set. There exists a linearly dependent set is a1 not equal to 0, a2 not equal to 0, all scalars is equal to 0. A subset of R models is said to be Li, every finite set subset is Li, LD set of LD is a basis. Pre-modules is a basis that a subset of R model is said to be basis. If B is Li and B is Li, B generates. So first a subset R modulo B is subset of R modulo M is said to be basis. B is a halide. Second, B is a generates. B is a generates of M. And is nothing but L of B is equal to M. L of B is equal to M. So it is M is equal to R2. Okay, M is equal to R2. So M is equal to R2 basis. So this is basis is 1 comma 0, 0 comma 1. So M is equal to capital F power of X. So basis is B is equal to basis is 1 comma X square. So dimension of R2 is equal to 2. Dimension of R power of N is equal to N. Dimension of F power of X. Dimension of a polynomial F power of X is infinite. So this is a infinite. Free models. Free model definition is an R modulo. So R modulo. So this is R modulo M is said to be is said to be is said to be is said to be a free is said to be a free modulo if M admits M admits a basis. M admit basis. Basis until we can do definition linearly independent and generates. And R model M is said to be a free model if M admits a basis. So example is M is equal to R2, M is equal to R2, M is equal to R2 is a free model, since R has a basis. M is equal to R power of N is a free model. M is equal to R power of N free model. Is a free model means an R model M is said to be